Wow, have I got something for you? This is the last presentation on parametric equations and calculus. It's part 3 and it's Bezier curves. We'll talk a little bit about Bezier, who was a mathematician and died in the 60s, 1960s. So, but have a look around the screen for the moment. Now, I've got a question for you. What framework is common to these curves? Well, hang on, what do I mean by that? What framework is common to these curves? Have a look around and see if you can see how Bezier set up a framework between which to create a curve using parametric equations. That's the basic idea. So what's the answer? Pause the presentation, study them carefully, and what do you notice? Well, I guess you can see there's a 4-point framework. Let's come to the first one over here. There are 4 points between which Bezier has got a curve there. A number of points dancing, if you like, according to the value of the parameter. And they're some fancy curves. Here, there's another one. They're indicating here you have 4 points between which somehow you're generating this curve. And here's another one. Okay, so interesting. And down here, down the left here, okay, can you see how this framework has produced quite interesting curves between them, some more interesting than others. What do you reckon about this one down here? What do you think about that? Can you see that it's 2 Bezier curves joined together here? Okay, and the starting and ending point of that one, the ending point of that one links up with the starting point of this one. That could be an interesting thing to do, to continue on that curve. Now, this is the basis really of computer-aided design, where you can produce a polynomial here. These are, in this course, we're only going to look at cubics for cubic Bezier curves, but Bezier and there were other people before him who actually discovered this, but he probably put his name to it because he used it most predominantly in design, design of car body parts, that sort of thing. And I think he worked for Renault back in the 60s, 1960s. So, geez, that, got to get rid of that. But there you are. What we're going to do is look at how he created these curves. And of course, you could create your own fancy curves like this using parametric equations. So let's go down and analyse what Bezier did. And there we have it. Construction of Bezier curves. There is an origin, okay, and a destination where you're going to finish up with your curve, and we have what we call control points in between. And what we're going to do is create a framework and then make the points dance between that framework. So the origin here is the starting point of the curve, and E, the destination there. And we can call these, in 2 dimensions here, x0, y0, and then x1, y1. That is quite common. x2, y2, and x3, y3 around the framework. You might say, well, hang on, how do you make this framework work? Okay, come down and let's have a look at the idea. And here it is, and some screen clippings here from Hayes and Harris publications, so you might have a look at that book. So here we are, to locate a point on a Bezier curve, one of those nice smooth curves and fancy shapes that we just saw up above. So first of all, what we're going to do is use a parameter t, but look at it over here. T is the ratio in which we're going to divide up a line segment. So we're going to call this f will be t as to t take 1. And then we're going to divide up C1, C2, t as to, oops, hang on, I just messed that up. It's 1 take t here, 1 take t, and you'll see why we do t and 1 take t in a minute. And h, we're going to divide into the ratio t, 1 take t. Okay, and we get these points now. We're at the point of f, g, and h using ratio division of a line segment. You can read the instructions over here. I'm going to do it. If we join now F and G, so we've joined those two, and G and H. We're going to do it again. We're going to divide F, G in the ratio T to 1 take T, and GH in the ratio of T to 1 take T. And then we're going to join those points I and J, so that we, again, guess what? This is T as to 1 take T. All right, and what do we produce after all that? We produce only one point, P. And what we're going to do is to say, well, as a ratio of division here, T will be greater than or equal to 0. If T is 0, it'll be back at this point. If T is 1, so it's greater than or equal to 0, I should put the whole thing, I'll put it all down here. 0, it's greater than 0, and less than or equal to 1. Okay, so our ratio of division here, T to 1 take T, makes sense. T can't be greater than 1, so here T would be 1. Now, this, and we're going to do all the T's in there. For all T, a member of R. Each T produces a point. It's dangling there, if you like. Now, if we did it again for a different ratio, then the next point might be somewhere over here, wouldn't it, if we set up the framework with a different ratio of T's around there? We'll have a look at that in a minute. Okay, so that's the idea of it all, and you want to just have a look at the equation for these points that are produced by those infinite number of divisions. So T is an infinite number of values between 0 and 1, and we create, therefore, an infinite number of points creating that curve. So that's quite interesting, isn't it? Using the parameter here, which is a property of this system, which is the ratio of division. Now, in a minute, I'm going to show you why we've used T and 1 take T. Come down and let's start working on the mathematics of it. So first of all, I think we've seen this earlier in vectors. If you want to divide a line segment by a point X in the ratio A to B, so let's just picture this here. We've got A, B, and X is somewhere in here, and it's ratio of A to B. Do you remember the X coordinate is A times the X of B up here? It's like a crisscross method. We proved this formula. This is a formula from, I suppose, a prior course, basic coordinate geometry. So it's A times that plus B times that over the sum of A plus B, and Y is the same. So it's the A times the Y value up here plus B times the Y value down here, divided by the sum. So that's a ratio of division formula, and that's the basis of how to divide up the framework and get that point dangling for different ratios. So we're going to change the ratio A to B in an infinite number of ways. So now, let's have a look. If X divides AB in the ratio T is to 1 take T, then what happens to the bottom line? Okay, A plus B in the bottom line would be 1. So Bezier decided to, instead of using a ratio like 3 is to 4, he wanted to use a ratio of, let's say, here, what have we got? 3 parts to 4. Have a go here, something in here, 3 is to 4. What would that be in terms of T? Okay, so this is 4 and a third times this part. 4 over 3 times that. And so what could you let T be? And 1 take T. T over T is to 1 take T has to equal 3/4. So here we could say 4T equals 3 take 3T, 7T equals 3. So T is 3/7 if you want to do it that way. Okay, so this would be 3/7, and this would be 4/7. Okay, so always going to be between 0 and 1 now, using that sort of system. But we can get an infinite number of divisions here with an infinite number of T values. Okay, so then let's have a look at what x would be in using t. So we'll do this again down here. A, B, x is going to be here. We've said that's t and that's 1 take t. So it's t times the x of b, there it is, and 1 take t times the x of a, and nothing underneath because a plus b is 1. So it's a tricky way, if you like, of removing the denominator from the expression for your created dividing point. Okay, so this is the idea over here, that if you want 3 is to 4, you'll use 3/7 and 4/7, if you like, in that ratio, so the sum is 1. And the bottom of that line, of that formula for the x and y coordinates, both of them, it disappears and becomes 1. So that's just a neat little tricky-do that he did there to simplify the working. But you want to have a look at the working. Come down now and have a look here. So going around here, if you want the x value of f, it's t times x1 up the other end, and 1 take t times x0. Then g's the same. T1 take t, it's t times x2, and 1 take t times x1. Oh boy, this is going to get complicated. Can you see how it will result in a cubic? Because we're going to do those divisions, 3 lots of divisions. So let's have a look. Over here it'd be t times x3 and 1 take t times x2. Now what we've got to do is go right around. We're going to do I and j next. Oh boy, this is going to get complicated. Come down and have a look. So I think we'll go right to the end there. So I, we're going to do I. So it's t times g's and 1 take t times f's. But look out, x of g and x of f were already complicated, weren't they, from the first division? There's x of g and x of f. X of g and x of f, correct. And then if we want to do h, it's this one by the, hang on, we've done h, we want to do j. Now this is t1 take t, so it's t of x of h plus 1 take t by x of g. Here it is. Well, that's all right, but look out, we've got to put in the x of h from before. Complicated looking expression. And the x of g, can you see how this is building up to a cubic in t? And then finally this point here, our dangling point, is the x value is t by the x of j and 1 take t by the x of I. Okay, so here it is, but by now this has become a big monster in here. The x of j is all of this, and then 1 take t by the x of I. So all of these have to be multiplied again by the final t. Now, I challenge you to actually expand that. I haven't done it here, it's not done in the book, but I have done it on the board with various classes, and it's a long process. But if you do that, you actually can group up your terms in t cubed, t squared, t, and a constant. So it becomes a cubic. Can you see how that is arrived at by those various line segments being divided? There are 3 phases: the outside framework, and then the lines created inside, and then the final one with P being on that last division. Okay, so this is what we've got to worry about. We're connecting the polynomial coefficients to the coordinates of the outside points, aren't they? The control points. We end up having these values dictating the coefficients of the polynomial and therefore the shape of the curve. So come down here, we'll just skip that a little bit and go just down there. Okay, so here what we've got is this. And if we wanted to say it as a polynomial, we could call that a t cubed plus bt squared plus ct plus d. And if you did, look at the mess that you've got to remember here for the coefficients of t cubed, etc., in terms of the coordinates of what? The end point, the second control point, the first control point, and the starting points, x coordinates. And of course, as with, I think, if you recall an earlier presentation, the cross product had a difficult combination, and we used a matrix method to determine over 3 by 3 to actually try to remember that. I'm going to show you a little thing here that's not in the book. Will help you remember that as well. And of course, if you went around again in Y land using the y's, of course you know the formula is the same for the ratio of division of a line with either in x's or in y's. So in other words, if this is t and 1 take t, looking at the y's, it's t of that y, t y1 plus 1 take 2 y naught, 1 take t y naught over the sum, which is 1. So it's the same procedure again, only with the y's around those points. So here, if we wanted the coordinates of the y values, y coordinate, sorry, of the point P, you would have the same idea here. Okay, so we're going to get the same numbers in these positions, okay, for t cubed, t squared and t. Okay, so how are we going to remember that? So let's come down and actually see what's going on here. So what we've summarised is that the ratio of divisions done 3 times now produce a cubic in t, where t is the ratio of division, t 1 take t in that format. And here you're going to get the same thing, the same dependence upon t. But of course they will be different because the x and y values of the points around there, around the controlling framework, are different. So here's our summary for the x's, and here's our summary for the y's. Okay, so the ratios are the same, but of course these coordinates are going to be different from the x coordinates on that controlling framework, if you like. All right, so this is what I'm suggesting to you. What about detaching those coordinates and making a 4 by 4 matrix? And then if we thought of it like this is an easy way of getting these combinations right here. Rather than saying, now what's x3, get it from the point, put it there. Then x2, get it from the point. Remember what these are. We're going around here. This is x0, y0. First control point, x1, y1. So it does matter that you're doing it in the right order. And x3, y3. So that's our pattern. Rather than trying to remember that, what about doing this? Let's watch this. This is an interesting use of matrices now. Okay, so if you put that there and did the multiplication, you've got a 4 by 4 and a 4 by 1. So you're going to end up with a 4 by 1, and these are the coefficients now, A, B, C, D down here. Okay, well maybe I'll put them in here, might be better, A, B, C, D. So this row dives down that column, so it's 1x3, take 3x2, plus 3x1, take x0. So that's that expression there for the A value. And then of course the next row dives down this column, so that's row 2, and entry here for this point here. So it's 0x2 plus 3x1, 0x3 plus 3x2, take 6x1 plus 3x0. It's this one here. So you can use matrix multiplication to most easily remember the combos that you need here and in the y values as well to get the coordinates of that dangling point, if you like. Okay, so you've got to remember that this is the system we're using around that. So we've got a starting point here and an ending point over here, and we've got 2 control points here. Okay, and of course, as we saw in the original window there of this presentation, we could start again with another one here and create another curve. We could have something in here and then something in here. Oops, it would go to the end here, and we might be able to make it as fancy as that or fancier. Okay, so that's the idea. So let's go down and have a look at what we can do. So here we are, we've got a bit of a calculator use here at the end as well, so I'll just bring that up. Okay, suppose we wish to find the Bezier curve from that to that with control points these two, and let's see what sort of curve we can make out of that by dividing it up. Okay, so here we've listed our x's and y's, and then we're going to do the calculation of what the polynomial looks like, because this gives us, remember, these are the coefficients of the cubic that we come up with. In other words, just remember the x value is given by this polynomial and squared and dxt plus dx. That's the x coordinate is given by that, and the y coordinate's got the same pattern here. So here it turns out that this one is 0, this one is 0, and this one is 0. So it's only a linear relationship to get the x value of that dangling point. So just remember what this means is, as you specify a particular value of t, you generate a point in x and y. And then you put in an infinite number of t's between 0 and 1, and it gives you an infinite number of points, and that's your curve. Okay, so over here, what would it look like? Come up here. We will put down here in reverse order. x3 is 3, x2 is 2, x1 is 1, and x0 is 0. And then if we multiply that out, we get 0, 0, 3, and 0. Okay, that's the idea. Just check, you want to just check there that works out correctly. Okay, so that's what they're doing over here, diving down that column matrix and using that multiplication to come up with the coefficient. Okay, and over here in y's, to remember the combinations, where are the y's? Here they are here. Put them in reverse order. 2, 4, 3, 1. And then when you go down here, you get the coordinate, the coefficients of the cubic, which gives you the y coordinate, and so that's going to give you -2, -3, 6, and 1. So just check those multiplications as you go down there and see that it works for you. So these are the coefficients of the polynomial now. So to get the y coordinate, it's -2x cubed, take 3x squared, 2x cubed, take 3t squared, plus 6t plus 1, and then you put into that, there it is there, you put into that an infinite number of t's, remember here, and you create an infinite number of points. Okay, so that gives you the y coordinate matching up with the x coordinate here to create that dangling point. All right, now I suppose what you might say is what does that graph look like if you try to graph it? And here we did it in an earlier presentation, last one I think. If you go to menu and choose graph and type parametric, and you put in the two equations, 3t, and just check your view window. You've got to have a correct view window there, so play with that, and you'll get this curve here. Okay, so you can see it's a pretty plain ordinary cubic, and that's, I guess, something you could look at here. The x value is just a linear function in time. Imagine how much you can make the points dance if x of t was something like 2t cubed plus 3t squared take 2 plus 1 or something. if that was also a cubic in t, and y was a cubic in t, you've got the points dancing around a lot more. You've got the relationships a bit more complicated than just a simple cubic like this. Okay, so you might think about that. Okay, we'll come down. I want you to do some in a minute. So here they are. And what you could do here, there is a program for most graphics display calculators where you, if you're not asked in a test or exam to show the working, now here it just says find the polynomials. So you could use a program that's been written where you introduce the starting point, the end point, the control points. So ask your teacher or other students about getting hold of that program for the graphics display calculator that you're using, GDC graphics display calculator, well, because it's a lot easier than doing what we've just done up there, where we've got what this is x0 and y0, this is x3 and y3, and here we are control point 1 and 2, so this is x1 y1 and x2 y2. So you'd have to set up your matrix to get those two expressions, two polynomial expressions in t for the x and y coordinate. Okay, now there is a program for most calculators which will allow you to do that. Now please note, if the question up here says you've got to show it or do it without technology, then you have to go through the whole polynomial thing like the example I've just done there with you. Okay, so here's a typical question. Here, what are the starting and terminating points on the curve? So that's, just remember, we start at t is 0, end at t is 1. Left and most and right points on the curve, highest and lowest. Left and right, just check this now. Left and rightmost points is the max and min for t. I'll give you a clue here. Max and min, for x, the t, that gives you a max and min x. Because remember, we're still talking about this. The left and rightmost is max and min x, and the highest and lowest points are still in y, so that's the max and min y. So now you can see why I've talked about it as parametric equations and calculus, because you're going to have to find the derivative of x with respect to t and y with respect to t to find the max and min, the most right and most left points on the axes there. So think about that. Okay, so t here means the ratio of division, and we've got a few other questions here. And there's an interesting one here. If we switch the parameter t for the Bezier curve, meaning time in seconds, you can determine the speed of drawing the curve at any point in time up to 1 second. That's an interesting twist, isn't it? So you can switch across and consider t, the generation of this, depending on t, but if t is time, then it's the speed of the generation of that curve. Okay, so we've got a little bit of velocity stuff in there, speed of the animation here. All right, so pause the presentation, have a go. The answers are down below. Let's have a look at this one here, question 5. Okay, here they're asking you to derive some of what we did before, finding the ratio of division there. So you're using the ratio of division, find the points. So you can't use a calculator for this sort of problem. It asks you to show that you can generate that curve. All right, and finally, question 6. This is fairly challenging. Prove that in the general case ij is a tangent to the Bezier curve at P. So you have to use the general form for I and j in x1, x2, etc. Here we are, giving you a hint here. This is a fairly long proof. Good luck with that. It'll take you quite a while to work that out using just general points there. Okay, and obviously can't use a calculator for that. All right, I'll show you the solutions now. So here's question 1 of that first set, A and B. And C. And question 2. can't quite get that in. I'll show you the bottom here in a minute. Part C, question 3, A and B. Here's an interesting point here. Check the boundary points to make sure they aren't higher or lower. And C. And question 4. And 5 is fairly long, it's that derivation, doing the ratio of division. Let's come down and finish that off there. And part B. And just finishing that question off. And then question 6 is fairly challenging derivation there. We'll just come down a little bit there. And finishing that off. So, yeah, that's a fairly challenging one. Let's move on. There's one little part that I'd like to finish off with here with Bezier curves, and let's come and have a look at it. Parametric equations of tangents to curves. Okay, so here we are. We talked a little bit about this before, that the velocity vector was a tangent to the curve at the point, and this was this idea here. The direction vector of the tangent is the vector which represents the rate of change of x at the point the rate of change of y. That was equivalent to what we talked about as the velocity vector. So here, this tangent has direction x dash a, y dash a. Okay. So what would its equation look like? So here we're going to call the equation, splitting into parametric form. If you take this to be a point on this as being, big X, big Y, then our X value is the X of A plus parameter times the direction vector. So this becomes our direction vector from what we established before. The tangent has a slope equal to the, has a direction equal to the derivatives of the x and y values at that point, x dash a, y dash a. Consequently, velocities there are tangential to the path, is what we established before. So the y value move out to the point y of a plus s, using a parameter s here, times y dash a. We're using s because generally the t will have already been used in describing the Bezier curve. So we've used t there, and now we want the tangent to it. So tangent at x is a, y is a. Let's do it the way I like it. The vector form, if you like, of a point on that is travel out to the point plus s times the direction vector, which is x dash a, y dash a. That's the idea, isn't it? Travel out to, so there's a vector travelling out to the point at which you want tangency, and then from there go in a direction of the parameter times the direction vector. And then of course you can get these parametric equations from that. So if you like to think about where that came from. All right, so and s is greater than or equal to naught here. Okay, can you see that it's going from that point in this direction? All right, so let's have a look at doing some, and here's an example from Hayes again here. So there's our curve, if you like. It's a Bezier type curve, and well, no, it isn't, because we've got t is 2 in this one. So x of 2 is 2 and y of 2 is 5, and we want the equation of the tangent to that. Okay, so we want it at this point. So what are you going to do? First of all, you need a direction vector, so get the derivative as 2t, take 1. And at 2, it will be 2 times 2 is 4, take 1 is 3. And here the y component of that direction vector is the derivative of y, so it's 3t squared, take 2t. And substitute it in. So what are we going to do? Let's think about what we're doing. We're going to travel out to any point on the line. So this becomes the vector equation equals travel out to the point 2, 5 plus s, because we've used t to mean a different aspect in this one, a different parameter there. So this is s times, what's our direction vector? 3, 8 here, the derivative. So then we can unpack it. 2 plus s times 3, here it is over here, 5 plus s times 8, or 8s. Okay, and we're talking about s being greater than or equal to 0 here, as it grows in the direction of 3, 8. Okay, so we're talking about a tangent to the point with a direction vector equal to the rate of change of x and the rate of change of y. So it's a tangent, a tangential position there. All right, so some of the things are linking up. It's important for you to stop and think about those and to retain what went on before. All right, let's go to the last exercise of this type here now. C6.3. Find the parametric equations of the tangent to the Bezier curve. So here they all are with t's less than or equal to 1. So you do the same thing now. Just remember that the tangent has a direction vector which is equal to the derivative of x's and y's at the point of tangency, as we proved before with the chain rule, or function rule, if you like, either of those. So I think you should do all of these. And here I don't know whether you've actually observed this as you've gone through, but SC1 and EC2 are tangents to the Bezier curve at those points. Okay, so you might try and prove that. This is a little bit of an extension. This is good for your thinking, ways of thinking about this. So try to do the tangent idea in general with just these general points here and see how far you get. All right, I'll show you the answers to those now. Oh, got to get rid of this. Okay, so come down. And A and B from question 1. C and D. And then question 2. So this is general proof now. We'll just go and finish that off. Okay. All right, I hope you're enjoying this. It's getting interesting, isn't it? Bringing in that other parameter can make things look a bit complicated, but can certainly be responsible for some good-looking curves and that. All right, so try and consolidate, and I'll catch you later on when we're going to look at the derivatives of trig functions. Cheers for now.